Okay, guys, can you guys hear me? Okay, guys, can you guys hear me? Okay, perfect. Let's give it one more minute while we're receiving more attendance. Okay. All right, it's 9:01, so let's get started. So welcome, guys. Welcome to our North American Math Competition lectures. For some of you guys, if you're familiar with our lecture basically can be classified into two major categories. The first category is the boot camp. I think pretty much most of the students already did before. So the bootcamp basically focuses a quick go through. We only have 10 lectures, and we're going to try to give you as much information as possible, hopefully give you guys a big idea what is the most important concepts for the entire math competition. Well, on the other hand, to the second category, we have the concept, or we say the knowledge-based lecture. So different from the bootcamp lectures, these kind of lectures are going to be more detailed. We're going to do something more granularly, give you guys the basic or the most important concepts for each session one by one. So our lecture actually organized during different sessions. Now we're going to focus on session 4, which is the circle and the coordinate geometry. So if you guys been to our previous session, session 3, you'll be knowing that we have already talked about the basic concepts for the 2D geometry. Basically focus on the triangles, the quadrilaterals, polygons, so on and so forth. All the technology we have learned in the previous session, something like the similarities, the congruencies, and also when you have like two parallel lines, you should be able to cut all the segments into the proportional parts. So all those kind of information are considered to be the foundation and the basic for all the 2D geometry. From today's lecture, we're going to go to the circle part. Circle will be considered as an advanced version of the 2D geometry, which consolidates all the important concepts we introduced previously, plus a lot of important flowery properties from the circle itself, and try to give you more important, more flowery problems. Okay, so in our knowledge concepts lectures, we basically focus on two things. First, we would like to give you guys some introduction about the basic concepts, the important theorems. This is actually for number 1. Well, number 2, I think, which is more important for our entire lecture, we like to teach you guys the strategies, how to think. Because you know what, fishing. I think thinking process, how do you think, is actually way more important than just read your answers. So from time to time, I'm going to be giving you guys what we call the conditional react. As long as you see a condition, you might be able to do some conditional react. And then just put all the conditional react together, sometimes just surprisingly, you see the answer right away. A lot of students keep asking me, hey, Alex, whenever I go to the AMC or go to our Canadian Waterloo exams, I see the last several problems are so difficult. And how do you really figure out what is the thinking process? You know what? My answer is that even though for complicated problems, these problems are actually composed by different easy problems. If you can really understand the conditional react for every single easy problems, put them together, trust me, the solution for complicated problem will speak for itself. So that's actually where it came from for this entire lecture. We just want to use our entire session to teach you guys this common sense, or we can say this conditional react. So from time to time, I will give you guys some heads up and let you guys know, okay, this is something important. You need to remember, you need to basically save it as a conditional react. So this is going to be like a learning process. Rome wasn't built in a day, and same thing applies to our math competition. We're going to hopefully using these 10 lectures during this journey, I can really help you guys to build up this conditional react gradually by gradually. All right, this is kind of like a quick warm up for our session. So if all good, let's go to our real lecture. In this lecture, this is going to be our session 4, circle and coordinate geometry. Okay, yeah, we're going to spend the first couple of lectures focused on the circle before we jump to the coordinate geometry. Okay, so today, let's go to our lecture number 1, circle basics. Okay, I think talking about the circle, you guys shouldn't be unfamiliar. We talk about circle from pretty much from your elementary school, right? The basic properties from the circle, you already learned and here and there, just pretty much maybe scattered all over the places. And one of the top goals for our lecture is to give you guys a very good summary. We summarize all those important concepts together and give you guys a kind of place you can always refer to in the future. All right, so let's go to the first one, is the definition. So what is a definition of a circle? I think pretty much everyone knows that it's a circle, it's a round circle, but how can I say that in a more mathematical way? So this is actually how we say that from a mathematical way. A circle is a set of all points in the plane that are at a given distance from a single point, which is the center, right? I think this is quite understandable, right? So this is basically a collection, or we can say a set, right? So try to use the word a set of all the points. So this is the basic definition I think everyone knows. Second, let's go to some basic terminologies. So what are the basic terminologies you're going to see in a circle? So also, I think this part of something so familiar to everyone, but we just take this opportunity, try to summarize everything as much as possible. The first one is an arc. An arc means that. Let's say I have a point A, I have a point B. An arc just means part of the circle. So this is an arc, part of the circle. So actually the arc can be classified into 2 different categories. As long as it's shorter than half of the circle, it has a name. As long as it's bigger than half of the circle, it has a different name. But this is not so important in our Canadian and American math competitions. As long as you know A and B, there's an arc, it's good enough. Okay. Number 2, chord. Chord means that as long as I have 2 points, let's say C and D, I make a connection between C and D. So chord will be considered as the segment which connects the 2 points in a circle. This is also so straightforward, right? Number 3, area. Of course, you know that, how to determine the area of a circle, pi r square. Number 4, circumference. Circumference is basically the entire length of the entire circle, right? that is going to be 2 pi r. These are so basic stuff. Number 5, secant. Secant means what? Let's say I have a point which is outside the circle. From the point, I want to make a line which cut the circle into basically 2 parts, right? And the left part is bigger one, the right part is smaller one. So AKA, the line actually has 2 intersection points with the circle. Let's say I want to give a name. This is maybe E. This is my L. So L is the secant. You basically cut the entire circle into 2 parts and the intersection with the circle at 2 points. Number 6 is tangent. Tangent means also you got a point maybe outside the circle, and let me change a different color. Let's say the E as well. This time you also want to make a line, but this line is actually intersecting the circle at exactly 1 point, right? So this is the point. I want to give you a name maybe F. This is L prime. So L prime is actually considered the tangent. I think these are so easy peasy understandable thing. Yeah, just a quick things I want to give you guys a quick note is actually the secant and the tangent. These are, okay, from the definition, these are 2 things. One is secant, the other is tangent, but actually they're the same thing. The tangent can be considered as a specific case of secant, right? So we can take an example as, let's say I have my secant here, this is my L, right? As long as my L is moving all the way, you see those 2 secant points. It's actually getting closer, 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 all the way. As long as you come to here, those 2 points will degrade into the same point, right? So therefore, a secant will be degraded into a tangent. I think these are quite understandable stuff. However, if you understand this, all those kind of flowery properties we will talk about in our coming courses, you will understand all the secant related properties. They're exactly the same as the tangent related properties. And tangent is only a degraded specific case of the secant. Okay, this is kind of like basic understanding for our entire stuff. So let's continue. Number 7. The radius, of course, everyone knows the radius, right? This is the radius. Okay, number 8. Number 8 is actually, I'm gonna go to a different page and drag you something new, okay? Number 8, what we call is a sector. So what is a sector? Sector is actually part of the circle itself. Let's say I have an entire circle, right? And then I just cut the circle like I cut a pie, right? So this is actually a secant. Number 9, central angle. Central angle. What is a central angle? You see, here is actually a central angle. A central angle is formed by using 2 radius, and the vertex of the angle stays at the center, right? The circle center, central angle. So this is actually theta. Okay, these are all very important but very basic concepts. I think you guys already know. The other one is inscribed angle. What is inscribed angle? Inscribed angle is a little bit different from the central angle. It is something like this. Let's say here, here. Okay, I'll give you a name maybe T. The inscribed angle means, okay, the vertex of the angle actually stays in the circle. And the other 2 sides, you're just basically using 2 chords, right? You use the vertex here, stays on the center, stays on the circle, and 2 chords to get this inscribed angle, which is quite understandable, right? This is phi. Okay, one very important thing I think you guys already know, there is actually a relationship between the central angle and the inscribed angle. And this kind of relationship will be used from time to time in American and Canadian math competitions. What is that? The relationship is in the same circle, in the same circle, if the central angle and the inscribed angle, they are facing the same chord, okay? They're facing the same chord. So you will have the inscribed angle is half of the central angle. Is that right? So two prerequisites. It has to be in the same circle, or the second is you have to face for the same chord. So basically, the inscribed circle, the inscribed angle is actually half of the central angle, right? There's also a very important thing here. Basically focus on this inscribed angle, and the central angle is same chord or same arc. They will yield the same inscribed angle, right? So a quick denotation is here. These are like the basics for the circle. Let's say I have a circle. In this circle, I want to highlight a part of this arc from A to B, okay? So taking from there, if I want to make one inscribed angle, this is C1. I want to make the second inscribed angle C2, the third inscribed angle C3, right? You'll be able to see C1, C2, C3. They are basically facing the same chord, AB, or you can also say facing the same chord, like same arc, AB, right? Because essentially they're facing the same thing. You will be able to see angle C1 equals to angle C2 equals to angle C3. Okay, so far so good. I think these are very basic concepts. I would just want to take this opportunity to summarize everything all together. All right, so let's continue. We're going to go to number 11. We're talking about some areas of a sector. Let's say previously we just talked about sector, right? Now I'm going to give you a sector. Let's say this is one of the sector. We have an angle theta, for instance. Okay, so if I want to determine the area of the sector, so the area of the sector will be pi r squared, which is the area of the entire circle, and then theta over 2 pi. Is that right? So as long as the theta is a specific portion of 2 pi, so this is the area of the sector. And what about I want to give you the circumference of the sector? So what are you going to do? So you have 2r. So the circumference, you have r, right? 2r, then plus this part, the length of the arc. The length of arc is pi times 2r, and then theta over 2 pi, right? Theta over 2 pi. Okay, these are like so easy peasy stuff. I think you guys should already know that from day one. So far so good? Perfect. If all good, let's go to our second part. The first part is basically all the important terminologies you need to know for circle. The second part, let's try to talk about some important properties of a circle. Important properties of a circle. Number one, we're going to talk about the chords of a circle theorem. What is a chords of a circle theorem? It goes like this. The perpendicular bisector of a chord passes through the center of the circle. Okay, what is that? Give you a graph and it speaks for itself. Let's say I have a circle. In the circle, I want to find you, maybe here is a chord, okay? If I want to make a perpendicular bisector means what? It is perpendicular to the segment, and also it cuts the segments into two equal parts, right? Or also we have another word to say this is a bisection. Bisection means this is something cut the segment into two equal parts, and also it is perpendicular to this given segment, right? So this perpendicular, let me try to use different color. Yeah, so the perpendicular bisector of this chord is gonna passing through the center of the circle. So that being said, these two parts are the same, right? I think this is quite understandable. And here I wanna give you a very important conditional react. Okay, in our math competition, from time to time, if you see a circle, you might see a chord and then give you some properties, so on and so forth. So this is a conditional react. As long as you see a chord, you try to make a perpendicular line to the chord. And also, if the question gives you the length of the chord, you must be able to determine the distance from the center O to the chord. Okay, this is something very easy, but they will be tested in AMC and Euclid and all those Canadian exams from time to time. Two things. As long as the question gives you a chord, most likely you want to make a perpendicular line to the chord, of course, from the center, right? So this perpendicular line will not only perpendicular, but also cut this chord into two parts. Number one. Number two, as long as the question gives you the length of the chord, then you can right away determine the distance from the circle center to the chord. For instance, I give an example. Let's say in this question, I give you the chord length is equal to A, for instance, then automatically you know this is A over 2, right? Because this is a perpendicular. And if you make a connection, this is going to be your R, with the radius of the circle. Then automatically using the Pythagorean theorem, you will be able to determine the distance from the chord and to the circle center will be under root R squared minus half of the chord, and then make a perfect square. I think these are so trivial, so easy thing, but trust me, this will be used from time to time. Later, I'm gonna give you some examples, and then you'll realize how important the theorem is. All right. Here, I wanna make another side note, talking about all the chords, and we actually talked about it before, as something, if in the same circle, this is actually a prerequisite, okay? You're gonna have the following conditions. If you have the same chord in length, this is gonna generate the same arc in measurement. This is gonna generate same central angle in measurement, and also the same inscribed angle in measurement. What is that? This is something very important, and Euclid and also our Canadian exams and our American exams just test it from time to time. Let's say I have a chord 1 and I have a chord 2, okay? As long as these two chords are the same in measurement, right? Like I mentioned here, same chord in length, then automatically these two, let me change different two colors, these two arcs are actually the same in measurement, right? Previously, we mentioned the same chord will facing the same arc, right? But now they don't have to be the same chord. They can be two chords, but as long as they're the same in measurement, so the two arcs will be the same, okay? And also the two central angles are also the same in measurement. Maybe it is theta 1, theta 2. So theta 1 equals to theta 2. The same, I mean, like the same length of the chord is going to generate the same central angle in measurement. Previously, we said, okay, if they are the same chord, they're facing the same what is called like the same central angle, but now they do not have to be the same chord as long as they are the same in measurement. It's good enough, right? And the last one is they're going to be the same measurement in the inscribed angle. So that being said, if I have an inscribed angle here, I have another inscribed angle here. This is phi 1, phi 1. This is phi 2. Right? You're going to have phi 1 equals to phi 2. Again, previously we said the same chord basically facing the same inscribed angle, but now they do not have to be the same chord. As long as they're same in measurement, even though they're different chords, they will also end up the same inscribed angle in measurement. Okay? I think these are so easy peasy stuff. Okay? Any questions, just let me know, okay? Because I'm actually monitoring the group chat all the time. As long as you have any questions, you can actually post your question into the group chat, okay? If you feel a little bit shy, which I don't think it is so necessary, you can actually send a private chat to me. So I will review your question and give you the answer directly. All right? So let's continue. This is actually the first one, right? The first chord of a circle theorem. Let's go to the second one. The second one we have already talked about, but just try to be more comprehensive. I just put everything here. Second one is the angle of a circle theorem. What is angle of a circle theorem is something pretty much we just learned. Just gonna highlight it one more time. Let's say you have an angle here. This is the central angle. And you have an inscribed angle here. They are facing the same chord or the same arc. So this is theta, this is phi. Phi will be theta divided by 2, right? So easy. Okay, here I want to make something very important. A quick note is from time to time, okay, this kind of chord, let's say this is A and B is my chord, right? From time to time, the question will give you some hint that the chord AB is not a random chord. It's actually a diameter, right? As long as you see the chord is not a random chord, it's actually a diameter passing through the center A and B, then automatically this inscribed circle will be 90 degrees, right? AB diameter, then you can say angle C equals to 90 degrees. And also this condition is sufficient and necessary condition. You can go from left to right. Diameter means 90 degrees, and also 90 degrees means diameter. If you guys are familiar with what we introduced previously, a lot of AMC problems like to do something like this. The question will never directly give you the angle for C. And also, it doesn't really mention the AB is the diameter, but with all those numbers given by the question, you can luckily and surprisingly find out, okay, angle C is actually equals to 90 degrees. And then automatically you will determine AB is the diameter and half of the AB will be the radius. So that is how it works for AMC. Sometimes AMC do not really give you some conditions directly. However, all those conditions will be hidden in the numbers given by AMC. As long as you do the calculation, you find out, okay, angle C equals to 90 degrees, then you can automatically tell, okay, AB is the diameter of the circle. Okay, this is all good. Okay, number 3. We're going to go to, this is very important, we call it tangent chord theorem. This theorem has been tested in Euclid, our Canadian exam, from time to time. So I think this is very important. Let's check it out. What is that? Let's see, I have a circle. And in the circle, I have a tangent. Sure. Okay. And from the tangent, I find another chord. Let's say something like this. Okay. So this is actually my circle. Let's say my circle O. I have a point, let's say A. From here, I make a L, right? I cut into maybe B. B is by tangent points. And then from B, I find another chord, let's say BC. And this is maybe D. Then automatically, I will find out angle ABC equals to angle D. So what is ABC? ABC, we give a name, tangent chord angle. What is that? Looks like the angle here has B as the vertex. B is the tangent points, right? And then what about the two sides? One side, I using the tangent line, okay? The other side, I actually use a chord in the circle. So this angle is actually inscribed by two segments. One is my tangent line. The other one is actually what? The chord. So we give a name, tangent chord angle. So the question actually, or the theorem actually says what? The measurement of this tangent chord angle is the same as another inscribed angle which is facing the same chord. Is that right? The question says what? The measurement of a tangent chord angle is actually the same as another inscribed. Right? This is an inscribed angle, which is actually facing the same chord. This is the same chord. Okay? Trust me, this is like so important thing. Okay? So how can we prove it? Do you know how can we prove it? How can I prove this tangent chord angle is the same in measurement as the inscribed angle which is facing the same chord? Wow, I think to prove it, this is not something so complicated. You can do a quick thing like this. Let's say, I'm gonna add an auxiliary line passing from O all the way to B. Maybe I'll change a different color here. And then all the way extension, make it extendable with E. Okay, then I just want to make a connection between CE. Okay, let's check it out. Now the EB is the diameter, right? So therefore, this part equals to 90 degrees. This is exactly what we just mentioned here, right? Diameter facing the inscribed angle, this angle is going to be 90 degrees. Okay, if this is 90 degrees, okay, so that being said, let's give a name, angle 1. So angle 1 plus angle E equals to 90 degrees, right? My angle E is here, my angle 1 is here. This is 90 degrees. Also, at the same time, don't forget a tangent. And if I do a connection between the center of the circle to the tangent point, OB segment is actually perpendicular to L. Is that right? You have a tangent line, you want to make a connection between the center of the circle to the tangent point. So this is going to generate a 90 degrees. So if OB is perpendicular to L, it means our ABC plus angle 1 also equals to 90 degrees. Angle 1 plus angle E equals to 90. Angle ABC plus angle 1 equals to 90. Those two things will say angle ABC equals to angle E, right? This is quite understandable stuff. The two angles, they're both adding one angle to 90 degrees, so these two parts are the same. Okay, and what about angle E? Angle E is facing the chord BC. angle D is also facing the chord BC, right? It looks like they're both facing the same chord. This is exactly what we just mentioned here. The same chord, right? The same length, the same chord, the same arc will yield all those same angles. So that being said, we're gonna do what? Angle E actually equals to angle D. So therefore, angle ABC equals to angle D. This is exactly what we need to prove. So QED, right? So this is a very quick proof, right? Quick proof. And please try to remember this condition. Like I said, the tangent chord angle is actually the same in measurement for angle, which is inscribed angle, which is facing the same chord, right? This is actually something very important. We're going to use that from time to time. All right, so far, so good. That's actually the third important property that we need to remember. Okay, number 3, let's go to number 4. Number 4 is we want to discuss a point and a circle. What are their positions relationship? A point and a circle, what are the positions relationship? I think you guys are very familiar with that. So again, I'm going to give you a circle, right? I'm going to find a point. The point can be here, can be here, can be here, right? These are something so easy. Let's say this is A, this is B, this is C. This is my center of the circle. So if a circle O, right? If the A is outside, so that being said, OA is greater than R, right? This is O, this is A, OA is greater than R. If A is on the circle, so OA is actually equal to R. If A is inside a circle, OA is lesser than R, right? These are so easy peasy stuff. And also, this is a what? A necessary and sufficient condition. From left to right, from right to left, you will be able to determine where the position is for this A point, outside, on the circle, or inside the circle. All right? But trust me, these are so easy, so understandable. From time to time, the math competition will not directly using such a condition to determine what is the position between the A and a circle. Actually, in the math competition, they like to use another way to denote the relationship for a point and a circle, which is actually using the angle. So how can I use an angle to determine the relationship from a circle to a point? This is something like here. Let's say, again, I have a circle, and I got a point, which is outside the circle or inside the circle, right? Now I'm just going to give one here. And I want to give thing maybe alpha. Okay. So now you have a circle. This is A, this is B, right? You have a point maybe P outside the circle. And you want to find another point, maybe C here. Okay. Now you want to find out the relationship of this P, right? And you can actually do something like this. From P, you want to construct that. Like basically the angle using A and B. A and B is the chord, right? And you want to find a point C on the circle. C must be on the circle. And from here, you can actually have a spread angle. A spread angle. What is a spread angle? Spread angle means basically you want to, from this point to spread, to look at the chord AB. So angle ACB, we can give a name, a spread angle. It's kind of like spreading, right? The two chords AC and CB, spreading. Okay, as long as you have such a relationship, if P is outside angle, then you will be outside the circle, then you will have angle P. It's actually lesser than alpha. If P is on the circle, you have angle P equal to alpha. If P is inside a circle, you will have angle P is greater than alpha. I think this is quite understandable as well, right? You see, here my P is outside the angle, is outside the circle. Of course, my P will be smaller than alpha. If my P all the way goes inside, this is P, right? If my P is all the way inside the circle, of course, my P angle will be greater than alpha. As long as my P is on the circle, maybe I'll change a different color. P is on the circle, of course, because angle alpha and angle P, they are facing the same chord, like we mentioned previously, right? As long as you're facing the same chord, you should have the same angle in measurement. That's good? So this is actually something quite understandable, right? Talking about the position of a P, which is outside, which is inside, and which is on the circle. Okay? So far, so good? Okay, since we have talked about the like a point for the circle, we then want to talk about basically the like a line and the circle's relationship and the circle to circle's relationship, right? So just try to be the completeness for the entire thing. Number 5, we want to talk about a line and the circle relationship. I think that part is quite understandable as well. We have already talked about it. So a line can be here. Let me change a different denotation. Yes, a line can be here. So that means the line has nothing to do with the circle, right? A line can be here, tangent to the circle. A line can be here, secant to the circle. But while these kind of 3 relationships, how can I use some easy peasy way to denote it? This is actually using what? The distance from the line to the circle. This is the first one. This is the second one. And this is the third one, right? So this is D1, D2, D3. As long as D1 is greater than R, so it means this line is actually outside the circle. As long as D2 is equal to R, means this is a tangent, right? As long as D3 is lesser than R, this is actually a secant. So far, so good. I think this is quite understandable stuff, nothing too flowery, right? So this is actually a relationship between a line to a circle. So we talk about a point to a circle. We talk about a line to the circle. Now we're going to talk about a circle to the circle. Number 6, circle and the circle. Circle and the circle, let's think about it. How many conditions we're going to have? We're going to start with something very far away. So these 2 circles, they're actually totally outside, right? So this is, oops, this is number 1, this is number 2. And then they're getting closer, closer. You can have the big one and the smaller one. They are tangent to each other, right? Oops. This is going to be tangent to each other. And then getting closer, you can have, they're actually intersecting each other, right? And then keep moving forward. I'm going to go to the other one. They're going to be what? Also tangent, but they are internally tangent, right? This is more like here, we can call it externally tangent, right? And this is actually internally tangent. And if you keep moving, at the end of the day, you can have they're totally, one is inside the other. That's pretty much all the relationships for 2 circles, and there's no other conditions. Is that right? Okay, so let's just check it out. What are we gonna do for 1 by 1 case? Oh, this is maybe O1, this is O2. In this case, if I want a connection between O1 and O2, you'll be able to see O1 and O2 is actually greater than the big R and the smaller r, right? What about the second one? They're externally tangent. O1, O2 will be equals to big R plus small r, right? O1, O2. And what about here? O1, O2 is actually lesser than big R plus small r, but greater than the big R minus small r, right? O1, O2. Then what about here? O1, O2. O1, O2 will be equals to the big R minus the small r. These are so easy peasy stuff, right? Big R minus small r. So you're just basically using the distance between the two circles to determine the range. This can be bigger than this, smaller than this, so on and so forth. And you will be able to determine the relationship between these two r's. And then what about the last one? O1, O2. So O1, O2 will be lesser than big R minus small r, then of course greater than 0. So this is actually all this position relationship between two circles, right? From their totally outside to externally tangent, they just intersect, internal ascendant, and all the way to one circle is inside the other circle. So these are also very easy peasy stuff, right? Okay, here I want to give you another very important conditional react. As long as you see two circles, they're tangent to each other. As long as you see two circles, they're tangent to each other. So you will be able to see such a thing. This is very important. One is externally tangent. The other way is internally tangent, okay? As long as you see two circles that are externally or internally tangent to each other, what you're gonna do is you're gonna make the connection between the two circle centers, number one. And second, you're gonna see that as long as you make this a connection, you will find out these connections, let's say O1, O2, they will be perpendicular to this common tangent lines of this two circle. Is that right? I'm gonna show you this one by one. See, I have two circles. These two circles are tangent to each other, right? As long as you see such a thing, you always want to make a connection between these two circle centers. Because as long as you do that, the connection between the two circle centers will be perpendicular to this tangent line of both of the two circles. So far, so good? So I'm gonna make a quick note here. As long as you see two circles, they're tangent to each other, then do two things. One is connect circle center, circle centers. Second, this O1, O2 will be always perpendicular to this common tangent. Okay, common tangent, excuse me, common tangent, right? Because this is quite understandable, right? You're gonna create such a auxiliary line. This is how you would like to create an auxiliary line. Later, you're gonna see in some problems, it's like so easy if you can directly using such a strategy. So trust me, all those common reactions, all those conditional reacts will be just try to be here and there. As long as you put them together, you can find out this is gonna help you to solve most of the problems. So any questions? I think somebody has a question. Isn't it greater or equal to 0? Oh yeah, this is greater or equal to 0. Yes, of course. Yeah, this can be equal to 0. Yeah, because means those, if they're equal to 0 means O1 and O2, they are actually superpositioning. I mean, they're actually sharing the same center. Okay, so far so good. Let's continue to number 7. Number 7. Number 7, we want to talk about the tangent of a circle. We just want to talk about the tangent of a circle. Okay, I have here, this is my circle, and I have a tangent line. Okay, all the way come to here, maybe another line, all the way come to here. Okay, so this is my, let's say P, this is A, this is B. From outside a circle, you can actually make 2 tangents to the circle, right? And there's only 2, you cannot make the third one. From outside of a circle, you can make 2, but only 2 tangents to the circle. They are PA and PB. And the measurement for these 2 tangents should be exactly the same, right? PA is always equal to P2. Like PA is always equal to PB in our case. Second, which is also very important, we can take it as a conditional react. As long as you see a tangent to a circle, your conditional react is connect the circle center to the tangent point. Always, always connect the circle center to the tangent points. Because by doing that, you're going to generate a 90 degrees right away, right? You're going to generate a 90 degrees right away. This is also a very important conditional react. It looks like, you see, all the way come to here, we have already give you several conditional react. And you can find out most of them focus on the tangent. You see, can be 2 circles tangent, can be a line and a circle tangent. You're just not surprised, because in most of the math competition, secant do not have too much flowery properties. Well, tangent is a specific form of the secant. So really in the math competition, they test way more on secant rather than the tangent. Okay? All right. So this is number 7. And we have 2 more things to go, and then we're going to do some real problems. Number 8. Number 8 is actually, we're talking about something like here. Let's say I have a circle, and my circle is actually inscribed for a triangle, which is quite doable, right? Let me change a different color. Okay, I have a triangle. My triangle is actually here. Okay, my circle is actually inscribed the triangle. I give a triangle's name. Oh, this is A, this is B, this is C. Okay, so this is side A, side B, side C, and my inscribed circle actually has a radius R. As long as you see such a shape, you should have a conditional react. Your conditional react is what? Your S, the area of the triangle ABC, will be equals to R times P. P is actually half of this perimeter of the triangle. Is that right? The area of this triangle is actually half of this perimeter times the radius of the inscribed circle. This is something so important. AMC, Euclid, our math competitions test it from time to time. And how to prove that? I think this is actually something quite understandable as well. You see, in order to prove that, we're going to do a quick proof. We can actually break our triangle into 3 parts. Okay, let me just use different colors to denote the 3 parts. Maybe this is the blue part, and this is the red part. And this is the green part. Okay, so what we can do, obviously, triangle blue area equals to what? This is R, right? is 1/2 r times c. C is the side length. Triangle red equals to 1/2 r times a. Triangle green equals to 1/2 times r times b, right? The area of the 3 small triangles can be written like here. And then I add them together. This is going to be the total area of my triangle ABC. Will be r times a plus b plus c divided by 2. Is it right? A times a plus b plus c divided by 2. So that being said, this is going to be our r here. It's the radius of the inscribed circle. And this is actually our half of the perimeter. Half of the perimeter. So far, so good? Okay, this is actually one thing. If the question just gives you a random triangle, this triangle has an inscribed circle, then automatically you should have such a relationship. Somebody will ask me, hey, Alex, what do I use for such a relationship? To be honest, the question barely asks you to use such a relationship to determine the area of a triangle because you already know the 3 sizes ABC, right? You don't really have to go such a complicated thing. You can just directly using the Heron's formula to determine the area of a triangle, provided the 3 sides are already given, right? So actually, this formula is more likely to be used in order to determine the r, or we can say the inscribed circle's radius of the triangle. So r can be written as S/P, right? You see? R can be determined as S/P. S you can actually use in the Heron's formula to determine P. P is exactly what you can do from here, right? So this is actually a more useful way to determine the inscribed circle's radius for any given triangles. As long as you know the 3 sizes, you'll be able to determine the radius of the inscribed circle. Okay? If all good, I want to make a quick extension. Now we're talking about a random triangle, right? I give a random triangle, I give you 3 sizes, and you will be able to determine the radius of the inscribed circle. But sometimes the question will not give you a random triangle. It might give you a right triangle. Let's say I have a right triangle. Also, I have my inscribed circle. Okay, also this is R, let's say this is A, this is B, this is C. Exactly the same thing. You can actually determine the radius of the inscribed circle a lot faster in the right triangle. R can be using A plus B minus C divided by 2. Okay, A plus B divided by C divided, A plus B minus C divided by 2. So this is what I'm trying to say, how to determine the radius of the inscribed circle. For a regular triangle, you have the basic formula, or for a right triangle, you have a shortcut. Okay, so how to prove this? I'll leave this as a homework. You can think about it. This is something very easy, so we don't want to spend too much time. Think about it, and you'll be able to get an answer. Okay, so far so good? This is number 8. We're talking about inscribed circle. As long as we talk about the inscribed circle, just basically using your intuition, using your intuition, you might be able to think about, what about I can do the circumcircle, right? So this is quite understandable thinking process. Now I have a circle inscribed in a triangle. Then what about I have something bigger? I have a bigger circle, and I have my triangle here, here, here. This is A, this is B, this is C. Okay, now Can I do something similar? Whenever I have this, do I have something similar? Let's say, actually, if this is R, let's say, right? Use R, you're gonna have such a relationship. The area of triangle ABC is actually ABC 4R. ABC 4R. This is actually something very important. Trust me, Euclid and AMC and our Canadian math competition is going to test it from time to time. If I have a triangle, so this triangle's area is actually determined by using the three sizes, multiply them together, divided by 4R. And 4R is actually considered to be the radius of the circumscribed circle. The circumscribed circle. So far, so good? Any questions? Okay, so people will ask me, hey, Alex, how can I prove that? This is A, this is B, this is C. In order to prove this, we're gonna use the Sine Law. So here I wanna, because we have some new student joining us, I wanna ask you guys, do you familiar with the Sine Law and Cosine Law? It's a question for you guys. Sine law and cosine law, we have already covered that previously in our triangle and quadrilateral section, and we're gonna reuse that from time to time in our basically circle sections. So can I ask everyone? Sine law and cosine law. Can I ask everyone to give me a quick feedback? I'd like to see where we are, okay? If most of the students are not familiar, I can just re-talk about it. No? Okay, no problem. Let's do a quick side talk about what is the sine law, what is cosine. This is actually very important. You have to know that in order to do the math competition. So, okay, in order to do this, we have to do the sine law and cosine law. So let's jump to the sine law and cosine law first. Sine law, cosine law. Sine law is something like this. Let's say I have a triangle, A, B, C. This is A, this is B, this is C. So sine law goes like this. A over sine A, B over sine B, C over sine C equals to 2R. So this is our sine law. It means what? A, this is actually the side length A, right? Over the sine value of this opposite angle. A is the angle which is facing the BC side, right? A over sine A equals to B. B is the side AC, right? B over sine B also facing pretty much the opposite angle. And also which is equal to C over sine C. C is actually here, my side AB over angle C. C over sine C. They both equals to 2R. 2R is what? 2R is the double side, is actually double of the, what is that? The circumcircle's radius. So if I create a circumcircle, let's try to use different color. So the circumcircle goes here, right? Any triangle, you should be able to create a circumcircle. So this is R, and this is going to be our 2R. Okay, this is our sine law. So far, so good? Any questions? This is our sine law. For the proving process, I can send you some message because this is outside the scope of our current session. In our previous session, we already gave you very clear explanations. So we have many students come from the previous session. We don't have to, do it for the second time. So this is actually our sine law. Okay, then what about the cosine law? Cosine law is pretty much the same. You have a triangle, A, B, C. This is A, this is B, this is C. So cosine law actually tells you what is the value for cosine A. Cosine A can be written as B squared plus c squared minus a squared 2bc. Cosine b, a squared plus c squared minus b squared 2ac. Cosine c, a squared plus b squared minus c squared 2ab. Okay, so this is the cosine law. So cosine law is what? You can basically, let's say I want to take this as an example. You can basically using the size, right? A, B, C, a different combination of the size to determine the measurement or determine the value of the cosine value for any kind of ABC triangles. But the cosine law looks like a little bit difficult to remember. You have so many a squared, b squared, c squared. How can you remember this? I'll give you a tip. I'll give you a quick tip. You never get what you need. You never get what you need. What is that? Let's say cosine A. You're determined about A, right? So you use b squared plus c squared minus a squared. And for the denominator, there's no a. It's only b and c. So you want to calculate a, but you never get what you need. There's no a here. Then what about cosine b? You want to determine the b. You have a squared plus c squared, then you need to minus b squared. And also in this denominator, you have no b's, a and c. Then what about cosine c? You want to determine c, but you need to a squared plus b squared minus c squared. Here in the denominator is only ab. So you never get what you need. So this is a shortcut to remember the cosine law. Okay, so far so good? Are we all on the same page? Yeah, any questions, just let me know, okay? So these are the sine law and cosine law. From any kind of math competition, they will test it from time to time, okay? Okay, so as long as you know this, you will be able to determine, okay, how can I say the area of triangle ABC is actually A times B times C divided by 4R. Let's say, I'm just gonna drag it here, right? I'm gonna give you the proof. Let's say I have my triangle here one more time. See, ABC. So if I want to determine this is A, this is B, this is C, right? If I want to determine the area of triangle ABC, I can use, let's say 1/2 A times C times sine B. Is that right? Do you guys know this? The area of a triangle, this is also what we introduced in our previous session, right? The area of a triangle can be determined by using the two sides, multiple them together, and also multiple the sine value of this included angle. So far, so good? Can I have some feedback? Because we have some new students here. I just want to make sure we're on the same page. Is it good? Because we're using some knowledge we learned previously to here. Oh, good? Okay, perfect. So 1/2 A times C times sine B. So, but I have a sine B here, right? I don't really like sine B. How can I deal with sine B? Let's check it out, check it out. We have our sine law here. So B over sine B equals to 2R. So therefore, sine B equals to B over 2R, right? This is quite, let's just do a flip. Okay, I'm just gonna replace sine B using B over 2R. You're gonna have 1/2 A times C, B over 2R. So ABC 4R. triangle ABC's area can be written as ABC over 4. That's it. Only two one-liner, QED. Okay? So trust me, these two properties are so important. AMC and our Canadian exam is actually testing them from time to time. There's actually no way around. You really have to remember, as long as you have, okay, let me just try to show you here. As long as you have a triangle inscribed in a circle, you have such a relationship. Okay? Again, like I said, most likely the question won't really ask you to determine the area of the triangle. It's more likely using the area of the triangle and ABC to determine the radius of the circumcircle, right? Okay. And the other one is here, as long as you see a circle is inscribed in a triangle, then most likely you're going to use this S equals to R times P to determine the radius of the inscribed circle. Okay, so far so good? Okay, perfect. I think that's pretty much what I want to say for today's lecture, talking about all the concepts, right? So we still have a lot more concepts I want to introduce. Let's save it for the future lectures. Okay. So after having all those basic concepts, I like to give you guys some real problems. Okay, so these problems are actually choose this problem from the Canadian and American and some from other nations, the European, Australia, like Chinese, all those kind of math competitions. Just trying to give you guys as much information as possible. Sometimes you will find out, okay, a problem from one math competition is almost the same as another problem from another math competition. Because this is not a magic, because all the concepts, they're actually limited, right? Even though different countries, when they create a problem, they're just essentially using the same thing, right? They cannot do something too flowery. So as long as you see much problems in advance, you should be able to solve the problem in a real math competition. Okay, so let's go to our second part, is the problems. Okay, today we actually focus on the basics for the circle, right? We're not talking about anything flowery. It's only the basic stuff. Generally speaking, when they test the basic stuff for the circle part, they just basically test you two things. One is the area. One is pretty much the circumference, or you can see like the perimeter or something. That's it, right? They just basically test you these two things, no more than these two things. So let's try to see some real problems. How are we going to test the area problem? How are we going to use the technology to solve the circumference problem? Let's go to area first. Okay, I think area is actually more tested more often than the second part. Let's go to some real problems. Yeah, for the first problem, we're looking at a problem that comes from 2003 Pascal problem. That's actually for grade 9, right? A Pascal problem. Let's check it out. Try to use all the technologies we introduced so far. We should be able to figure out. This is a problem from question number 22. Okay. So the problem says, in the diagram, two circles with center A and center B, they are intersecting at points P and Q, such that PAQ equals to 60, PBQ equals to 90. So I think this is a good habit. It's a good like a practice if you just try to highlight all those important information given by the question, right? Okay, so what is that? Let me try to highlight it. PAQ equals to 60. This is 60. PBQ equals to 90. This is 90. Okay. So the question is asking, what is the ratio of the area of the circle with center A to the area of the circle with center B? So basically you want to determine S01 over S02, right? Okay. How can I How can I do this? So this is kind of easy problem, right? So let's try to use this to basically teach you some thinking process. How do you think? Which is the most important thing. Okay. So the question give you such two circles, they're intersecting each other, and then they want to ask you to determine what is the area ratio, so on and so forth. In order to determine the area ratio, everyone knows that you're going to do pi r square, pi small r square, right? Basically, you want to determine the r, the big R and the small r. Everyone knows that. But in order to make sure you can find the big R and the small r, you want to find out the relationship between these two shapes. If they're not talking to each other, how can you do anything, right? You want to make sure to talk to each other. Okay, how can I make sure these two circles talk to each other? This is actually $1 million question. So for the left-hand side, this is big R. For the right-hand side, this is the small r, right? Everyone knows that. But I need to make sure they talk to each other. At the end of the day, all those kind of like geometry problem, you need to put them into either triangles or maybe quadrilaterals to do your work, right? You cannot really let all those segments fly in there before you can do the work, right? So the $1 million question is, how can you build up the relationship between the big circle and the small circle, and taking from there, solve the problem? This is something you need to ask for yourself. The relationship. Do you have a most straightforward way for them to build up a relationship? I think it is. You know what? Do a connection for AB, right? And then you kind of having an APB, which is actually what? Which is actually like a triangle. And also, you want to make a connection to PQ. Why? Because that is being said, you will be able to create a triangle, right? And then taking from there, you might have some properties and so on and so forth. So I think this is quite understandable. Okay, as long as you do here, I think you're almost done for this problem. Let's try to drag out. This is A, this is B, this is P. By using this symmetric property, this is going to be 30 degrees. This is going to be 45 degrees, right? Because this is 60, this is 90. They're all symmetric. You cut them as a half. So basically, you have 30 degrees and 45 degrees. And also, think about here. Because this is 60 degrees. And this guy equals to this guy. They're all R. Is it right? So that being said, my triangle APQ is actually what? APQ is actually an equilateral triangle, right? Isosceles triangle for sure, because you have two R's, plus you have a 60 degrees. A 60 degree isosceles triangle is going to be what? Equilateral triangle. Okay. Also, you're going to find out, check it out from here. This is actually what? 30 degrees. Let me try to change. This is 30. Change the color. This is 30. This is 30. This is what? An equilateral triangle or isosceles triangle. This guy will be not only a bisector, but also a perpendicular line, right? The top angle's bisector is also going to be a height for the bottom, right? So this is going to be a 90 degrees, right? This is quite understandable. So that being said, let's check it out. You are looking at something like this. This is 30 degrees, this is 90 degrees, and this is 45 degrees. If this is R, for instance, so this is going to be R over 2, right? This is a 30, 60, 90 degree triangle. This is R over 2 under root 3. If this is R over 2, this is also R over 2, right? And this is going to be R over 2 root 2. Don't forget, this is your small r. Is it right? So easy, right? You just try to play with the basic properties from the left to right. So you will know the small r equals to r over 2 root 2. So r squared equals to 1 over 2 big R squared. So therefore, if you have this, you can plug in here. Big R, okay, this is R, right? Big R squared plus over small r squared is going to be 2 over 1. So the solution is D part. So easy, right? This is an easy problem, but an easy problem also reflects some very important mathematical thought, right? So as long as you see two circles, at the end of the day, all your thing must be done by either a triangle or quadrilateral, so on and so forth. Then try to build up the relationship between the two circles, and you'll be able to solve the problem. Is that right? Build up. How can you build up relationship? Of course, do a connection, and taking from there, you'll be able to solve the problem. So far, so good. This is only a warm-up question. Okay, if all good, let's go to a second problem. Our problem is like, okay, I'll show you is progressively. The second problem we're looking at is a problem that comes from 2005 Katie question. Katie is actually for grade 10, right? But trust me, even though for grade 10, these are so understandable as long as you know all the technology we introduced so far. So this is a problem from 2005, Katie, question number 10, and like grade 10, question number 22. So the problem says what? In the diagram, AOB is a quarter circle. Quarter circle, you need to really highlight it. Like I said, always try to highlight the most important condition. Quarter circle means angle O equals to 90 degrees, right? A quarter of 360. Of a radius 10, okay? The question gave you the radius. And the PQRO is a rectangle of a parameter 26, okay? A rectangle parameter 26, okay? With all those information, the question asks you to determine the parameter of the shaded area is what? The parameter of the shaded area. How do we think as long as we see such a thing? If the question asks you to determine the parameter of the shaded area, you need to know the AQB arc, right? And you need to know AP, BR, and you need to know the PR, right? With all those 1, 2, 3, 4 parts together, we're good to go. And what is given by the question? The question already gives you the radius is 10. And also the parameter is 26. Okay, so that being said, let's check it out. AQB, I think this is doable, right? AQB is exactly just what? Just 2 pi r times 1 over 4. Is that right? So that one is actually 5 pi. Okay. AP plus BR, maybe we'll think about later. Can you tell me what's the value of PR? Who can tell me? Fairly quick. What's the value for PR? Who can tell me? What is the value for PR? Yeah, PR is exactly at 10. Why? Let's see, Ethan Benjamin, they have the answer right away. Because PR is actually equal to OQ, right? The two diagonals for a rectangle are actually the same. And OQ is basically my radius. So this is equal to 10. Okay, they're all check. So it looks like the $1 million question is I need to figure out what is the value for AP and what is the value for BR. This is, you always need to ask for yourself all the way to come to here. Did I use all the conditions in the problem? or some condition is left. I didn't use the condition yet. Obviously, this condition I didn't use yet, right? The perimeter of the rectangle is 26. I didn't use it yet. Okay, in order to use the perimeter of the rectangle, I basically have to use the two sides. OP, let me try to take it from here. If you want to use the perimeter, you need to have OP or you need to have OR. Otherwise, how you're dealing with the perimeter, right? So that being said, means what? Whenever I'm trying to deal with the value for AP and BR, I must get OP and OR involved in order to use it, in order to solve my problem. See, this is the thinking process. How do you think? This is not a difficult problem, it's an easy problem, but I really like to show you this kind of thinking process. So it means that I have to use OP, I have to use OR in order to get involved the parameter and taking from there, solve my problem. So AP plus BR, okay, if you really ask me to use, I'm gonna use AP equals to AO minus PO. So I'm actually using it. Since you're asking me to use, I'm gonna use it. BR is BO minus RO. So that being said is what? AO, BO, these are actually 2R, right? The minus PO plus RO. PO plus RO equals to what? Half of the parameter given by the question. Is it right? So that one is going to give you 2R is actually 20. The minus, I think, is 13. So this is actually 7. So that's it. This part is 7. 2 pi, 5, 5 pi, 7, and the 10. All the way, you're going to choose the C part. You see, this is also an easy problem, right? But the thinking process is very important. How do you basically use whatever you know to determine whatever you do not know? Try to build up the relationship between all the conditions and you're good to go. Okay? So far, so good. So this problem is talking about the parameter. The area and parameter, they will be basically testing one or another. If all good? Let's go for another problem. We're going to see a problem that comes from AMC. Oops. Number 3, it's an AMC problem. We're looking at a problem that comes from 2016, AMC 10A, question number 21. Okay? It's pretty much the last 5 problems. So the problem says circle with center P and Q. They have a radius, a PQ and R, they have a radius 1, 2, 3. Okay, 3 circle has 3 radius. Okay, respectively. They lie on the same side of line L and the tangent to L at P prime, Q prime, R prime. So basic 3 circles, right? They're basically lying on the same side. They're all tangent to line. Okay, the circle with center Q is externally tangent to each of the other 2 circles. Okay, so I give a feeling something like this. You have a 1, 2, 3, right? They're basically doing something like this. This is my P, this is my Q, this is my R. One is bigger than the other. 3 circles, they are tangent to each other, and they're all tangent to the line L. With all those information, the question asks you to determine what is the area of this triangle formed by 3 different circle centers. What is the area of the triangle formed by 3 different circle centers? You know what? In order to solve the problem, I think we need to have a better shape, like a more kind of like an accurate graph, right? So I have already drawn you the graph. I'm just going to put it here. This is the graph. Okay, so I think this graph makes much better sense, right? You have 3 circles. The 3 circles have the area. This is, oops, this is radius 1, this is 2, this is 3. And they're all tangent to each other, right? And the question asks you to determine for this PQ, the very slim area, the very slim triangle, what is the area for it? Okay, how can I do this? This is, right? I need to basically determine what is the area for this triangle. I don't think you can directly determine the area of this triangle solely using our geometry way, our 2D geometry, because they're totally they're totally flying there, right? And you're not really touching one another. As long as you see such a problem, I think the thinking, again, I'm teaching you guys the thinking process. If you see a triangle which is tilting there, flying there, it has not touching the ground. So most likely you directly want to determine the area, you want to find the bottom, you want to find out the height. This is impossible. So maybe we can change our way of thinking a little bit. Let's try to do some manipulation. Instead of directly calculate out the area of the triangle, maybe I can use some other shapes, adding them together, subtracting them together. Hopefully, I will be able to construct out the area of that triangle. How can I do that? The condition does not give me too much thing. There's only 3 triangles, 3 circles, that's it. However, let's check it out. If you have already know the area of this trapezoid, let's check it out, the blue trapezoid. Okay, so this trapezoid contains part of this triangle, right? Not all, but part of this triangle. And then you want to determine the area of the second trapezoid, the red one. So let me try to finish this first. If you can determine the area of the second trapezoid, okay, then you're kind of covered, right? Then you're kind of covered this triangle in 2 shapes, right? The blue one and the red one. However, you're overcounting a lot, right? The question really asks you to do the PQR, but you are actually counting too much. Then, that being said, why don't you subtract the area of this black triangle, this black trapezoid afterwards? I'm just gonna put it here. This is the black one. Is that right? You can actually use the, okay, I'm gonna do that after I'm done. Okay, I think a quick observation says you can add the blue one to the red one and then subtract the black one, and you will be able to determine the area of those pretty slim and tilted triangle. So far, so good? So I'm just gonna write it here. So the triangle's area equals to the blue one plus the red one minus the black one. Okay, so our goal is try to determine what is the area for the blue, for the red, for the black. Okay, let's jump to the first one, the blue one. The blue one, in order to determine the area of a trapezoid, you need to know the bottom, you need to know the top, and also the height. The top and bottom is already given by the question, is 1 and 2. So how can I determine the height? P prime, Q prime. As long as we figure out the prime, we're good to go. Who can tell me, how can I figure out the height of the blue prime?
The Pythagorean Theorem thing uses the radius of P and Q, and then use the Pythagorean Theorem thing.
Okay, perfect. Thank you, Ethan. Yeah, that's a very good direction. But why we want to go for that? I think if you can still remember our conditional react, we said, as long as you see two circles that are externally tangent to each other, you try to do the connection between the two circle centers. This is exactly what we mentioned previously. Still remember? Conditional react. Okay, so this is 1. Change the color to red. This is 1. This is 2. So that being said, if I do a Pythagorean, this is also 1, right? This is 1, this is 1, this is 1. So you have 3 here, you have 1 here. So this is going to be what? Under root 8, right? It's actually 2 root 2, right? 3 square plus minus 1 square, you're going to have the height for the blue triangle is 2 root 2. So the area is 1 plus 2, 2 root 2 divided by 2. Then what about the second one? Exactly the same thing. You want to do a height. This is 2, this is 1, right? This is 2, this is 3. Using the Pythagorean, this is going to be what? 2 under root 6. Excuse me, 2 under root 6. So this is going to be 2 plus 3, 2 under root 6, 2. The black one is the same thing. You already have 2 under root 2, 2 under root 3. So the 2 under root 6, the total is 2 under root 2 under root 6. So this is 1 plus 3, 2, 6, 2. Okay, basically adding them together, subtracting them together, you have answer under root 6, under root 2. That's it. See, fairly understandable. There's nothing so flowery, right? Okay, here, I think that this problem is done, it's fini, right? So before we jump to the other problem, I'd like to give you a quick side note. Actually, to solve this problem, the most conspicuous way, to be honest, is not using this entire 2 trapezoid, adding them together, then subtract the other trapezoid. The most straightforward way, or the most conspicuous way, is actually using the coordinate geometry. Since we're not talking about coordinate geometry for today's lecture, but later, after we finish our entire session, you should be realized to solve this problem, your first conditional react is never using trapezoid. Actually, you should using the coordinate geometry. I'll give you a very quick side note, because you don't really have to know this today. You will know that later after we finish our entire lecture. I'm just going to drag this one more time, then you will understand where I come from. Okay, oops, just going to, oops, drop it one more time. Okay. You know what? The most intuitive way to solve this problem is actually you need to create a coordinate. From here, this is y, this is x. And you need to figure out what is the coordinates for the 3 points. I think for P it's easy, right? 0, 1, right? For Q is exactly the same thing. You have already know this part. You have already know this part. So Q can be under root 2, 2. 2 under root 2, 2, which is quite doable, right? And the R can be under root 6, under root 2, 3. Okay, as long as you know the 3 coordinate sides, the 3 coordinates of a triangle, then you will be able to determine the area of the triangle directly using the shoelace theorem. Okay, we will talk about it in our entire session, but I just want to give you guys a quick forecast. Normally speaking, this is the most intuitive way to solve the problem. So a quick question, ask you guys, have you guys heard about the shoelace theorem? Can I do a quick survey? Have you heard about shoelace theorem? No? Okay, no problem. No worries, because we're not going to talk about today. We're going to talk about later in our lecture. Okay? So what I'm trying to say is that sometimes some very complicated geometry problem can be solved using the coordinate geometry. So the coordinate geometry can really help us to simplify the thinking process a lot. Because in this problem, you really have to figure out how to add these two trapezoids together and then subtract another trapezoid. If you think about it, you're good to go. If you do not know how to think about it, you're stuck. However, as long as you know the coordinate geometry, all those complicated thinking process can be simplified using calculation. Because thinking is expensive, right? Sometimes some world-class problem, it took years for people to think out. But calculation is cheap. If you do not know how to do the calculation, the computer will calculate for you, right? You use like 2 years to calculate, computer maybe use 2 seconds. So in the future, the big trend for our entire mathematics is actually to save the people from the heavy calculation. Let all the calculation go to the computer and convert some very complicated high-level thinking problem into a heavy-duty calculation problem, because the computer can always help you to do the calculation. This is only a quick side talk. If you're not 100% understand what I'm trying to say, like the shoelace or something, no worries, because we're going to talk about it in our entire lecture. So here, just want to give you a quick forecast. Our geometry and our coordinate geometry, they're bind. They're not totally one after another, not talking to each other. They're bind. Okay? If all good, let's go for another problem. Another problem, I also like to take a problem from AMC. This is actually open 1, 2, 3. There you go. That's another problem we got from AMC. It's a problem that comes from 2017, AMC 10B, question number 21. Okay. The question says, in triangle ABC, you have AB, AC, BC, okay? And D is the midpoint of BC. Okay, let me give you this 3 sides. And D is the midpoint. And what is the sum of the radius of the circle inscribed in ADB and ADC? Okay, before we jump to the calculation, let me ask you a quick question. And this is actually something very important. Now, the question gives you A, B, C, AB, AC, BC, 8, 6, 10. Before we jump to the calculation, these 3 numbers, does it make anything special to you? Or they're just like a random numbers, 6, 10, 9. Did you see the 3 numbers give you anything kind of like special? Yeah, I see a lot of students have the right answer right away. This is actually what? This is a Pythagorean triple. That being said means ABC is not a random triangle. ABC is a right triangle. Is that right? Trust me, this is extremely important. Did you still remember what we mentioned previously? If you check your note. Previously, I mentioned what? You see? Something like here. They give a right triangle, and taking from the right triangle, you want to do something. But like I said, most of the time, the people will not directly tell you this is a right triangle. You need to figure out the right triangle by yourself. Same thing. If you check your notes, this is exactly what we mentioned previously. Here, I also mentioned, if we know the right triangle, we know the AB is going to be the diameter, right? And vice versa. But most of the time, the people or the question will not directly tell you this is a right triangle. You need to do some calculation and figure out, yeah, this is a right triangle by yourself. This is actually something very important. So in the entire AMC and our Canadian exam, most of the time, you need to pick up all those Pythagorean triplets by yourself. The question won't directly tell you this is a right triangle. So try to remember all those very important Pythagorean triples, and you should be able to good to go. Okay? So let's go back to here. Okay. So, okay, let's go back to here. Let's go back to our question. Okay, so this problem is not a random triangle. This is a right triangle. So I'm just gonna draw the right triangle. Okay, and you have a midpoint for the BC. No problem. Here. So this is gonna be what? A, C, B, D, right? And what is the sum of the radii of the radii of the circles inscribed in ADB and ADC? So I have a here, I have a here. Okay, sorry about my drawing. So this is R1, this is R2. Okay, so how can I determine the radius? You have a triangle, you inscribed a circle, it's time for you to determine the radius. This is exactly what we mentioned previously, right? We mentioned that, come here, don't forget. Yeah, voila. This is where we mentioned, right? So as long as you have a circle inscribed in a triangle, so you will be able to determine the area using R times P. But like I said, most of the time, you don't really need that. You want to actually using the S and P to determine the radius. And this is exactly what the question asks you to do, right? So let's do this, let's do this. S equals to P times R, right? P is ABC divided by 2, right? Okay, with that information, how can I determine R1? How can I determine R2? How can I determine R1? How can I determine R2? You know what? This is a kind of easy problem. Let's give you maybe 1 minute. I'll wait for your answer. Okay, tell me what is the correct answer for this. 1 minute. I need to get your, I really want you guys to get your hands dirty, right? So let me know when you have the correct answer. Yeah, I see somebody has the correct answer already. Yes, the correct answer is D, 17/6. Okay, you guys all get answer? 17/6. I think it's easy, like the calculation is not so difficult, right? So basically, you have this triangle AB, AC, CB, right? And you will be able to determine what is the length of AD, because AD is the median of the hypotenuse. In any right triangle, the median of the hypotenuse is actually half of the hypotenuse, right? AD is 1/2 of BC. Do you guys know this? Any right triangle, the median of the hypotenuse is actually half of the hypotenuse. So you know this is 5, this is 5, right? So let's say for triangle, the first one, R1, you want to determine R1 in this triangle ACD, right? In this triangle ACD. So according to our definition, R1 will be equals to S over P1. S, how to determine S for this little triangle? You really do not have to use the Heron's formula. So the little triangle, like the red triangle's area is only 1/2 of the big triangle ABC. Is it right? The red triangle's area is actually 1/2 of the right triangle ABC. 1/2 of triangle ABC. And the half of the parameter is actually 8 plus 5 plus 5 divided by 2, right? R1 will be, and what is R1? 4/3, right? And how to determine R2? R2 is exactly the same. Let me just change a different color. It's here in this green triangle, right? In this green triangle. And this green triangle, R2 is exactly the same thing. Oops, change the color. R2 will be S over P2. S is also 1/2 of the big triangle ABC. And P2 here is 5 plus 5 plus 6 divided by 2. I think the answer is 3/2. And then you just do a subtraction, you get what you need. You see, the thinking process per se is also very understandable, right? Nothing too flowery, nothing too complicated. So far, so good? If all good, let's go to the last problem for today's, okay, student guide question. Why ACD is half of the ACB? Yes, that's a good question. Because this is, let me change a different color to black. Because this is the mid. So the red triangle and the big triangle, they are sharing the same height, right? However, the bottom here is only CD, while this bottom is BC. So therefore, the red triangle and the green triangle, they have the same area, right? And the red triangle is half of the big triangle ABC. Does it answer your question? Okay, yeah, any question, just let me know. And because we're using a lot of things we talked about previously in our previous session, session 3, if you're a new student, you're not so familiar with everything, no problem, just let me know. All good? If all good, let's go to the last problem for today's lecture. We're gonna look at a problem that comes from format. I like to give you guys a problem pretty much from all over the places, and you'll be able to see, oh no, not this problem. I'm gonna copy it. All those Canadian problems from all over the places. 1, 2, 3, yeah, that's the format problem. That is a problem that comes from 2005. Format. Format is for grade 11, right? But trust me, all the technologies using here are so straightforward. Everything we have already covered, you should be easy. This should be easy peasy for you to do it. Let's check it out. So the problem says in the diagram, a semicircle has a diameter xy. Rectangle, so this is a rectangle. PQRS is inscribed in this semicenter with PQ equals to 12 and QR equals to 28. So the question already gave you the two sides of this rectangle. A square, okay, you have a square. STUV has T on RS, U on a semicircle, U on the semicircle, and the V on the XY. So basically you squeeze in another square there. With all those information, the question asks you to determine the area of STUV. So let's check it out. So this problem, you have, you have this is 12, you have this is 28, right? And this is actually a square. So this is S, right? O square. And with all those information, the question asks you to determine square's area. Again, I like to show you guys the thinking process. How do you think for such a problem? Apparently, you need to determine S, right? But again, in order to determine S, like I said, you cannot determine S just randomly in the middle of nowhere. You must find out the relationship between S and the other, like maybe 12 and 28, right? And taking from there, hopefully you can solve the problem. And the most important thing is basically you need to put everything into triangles. If they're not in the triangles, there's no way for you to solve the problem, right? We're all on the same page. This is for one thing. You need to construct triangles. Second thing, you are in a circle. In order to do the job in a circle, most likely you're going to create radius. If there's no radius, how can you do the circle thing, right? So two conditional react. Number one is basically put everything into a triangle. Number two is you must create all those radius. As long as you have these two things, you'll be able to do the work. So far, so good? Okay. First thing first, let's try to think about it. How can I create a radius and how can I create triangles? I think this is not something quite magic. You just basically find out the center. Do a connection from here. Do a connection from here. This is R, this is R. Because first of all, you find your radius. And second, because you want to deal with S, right? You basically want to create some triangles, and taking from there, you might be able to do the work. I think this is quite understandable. Okay, so which triangles you're dealing with? I think these two triangles are good enough. One is the red triangle. The other one is the green triangle. Green triangle. We're good to go. Why? Let's check it out. Let's think about it. How are we going to do? First thing first, in this entire graph, you have two variables. One is R, one is S, right? So two variables, most likely you need two equations. As long as you have two equations, you're good to go. So I need to create two equations in order to contain these two variables, and then my work is done. How can I create these two equations? Most likely, I'm still going to use the Pythagorean theorem, right? You have so many right triangles, right angles here, right triangles here as well. So let's think about in the red triangle. Whoops. In the red triangle, what you have? You have, this is 14, right? And this is 12, right? OS equals to 14. This is half, right? Everything is symmetric. And RS is equal to 12. So therefore, R squared equals to 14 squared plus 12 squared. Is that right? Easy peasy. And in this green triangle, what you have? This guy is going to be 14 plus S, right? Because this is S. This guy is S. And this is R as well. So therefore, you're going to have R squared equals to 14 plus S squared plus S squared. Is that right? This is quite understandable, right? We're not talking about any magics. So now you have two equations. Equation number one, equation number two. The first equation can help you find out the value for R, and then you plug it into the second equation, and you will be able to determine the value for S. This is not a magic, right? So I'm going to help you to do that. R, this one actually equals to what? R is equal to, R squared equals to 340. And then you're just going to plug in here. 340 equals to 14 plus S perfect square plus S perfect square. So do some simplification. You're going to S square plus 14S minus 72 equals to 0. S equals to minus 18, or S equals to 4. Of course, minus 18 should be dropped. So we only have S equals to 4. As long as S is equal to 4, you should be able to see the area of STUV, the little square, equals to 16. Voila. You see, grade 11 problems are so easy. As long as you know all the technology we introduced, we should be able to solve it out fairly quick. Okay? Okay, so that actually wraps up our today's lecture. Let's do a quick recap what we have learned today. Today is the first lecture of our circle basics, right? In this lecture, we actually give you guys a quick summary about all the important and properties for the circle. I think most of them you have already know, right? But just try to, for the sake of being complete, we give you guys all those information at one shot. We do the definition, we talk about all those terminologies, and also those important theorems in term, right, in the circle. And also in the course, we give you guys a lot of conditional react. Hope you guys can remember this conditional react, because as long as you place them together during a math competition, most of the time the problem will speak for itself. All right, so hope you guys enjoyed today's lecture, I'm going to upload our assignment into our Google Classroom. You have 1 week to finish the classwork, and then we're going to see you guys for the next week. For the newcomers, a quick note is, as long as you do a good job, in the next week, I might be asking you guys to give us a quick presentation. So just basically ask you how to solve the problems. So as long as I ask you, means you're doing a good job. So I won't make you like a fool in front of everyone. So don't be shy. If I ask you, means you have the correct answer. All right, I think that's pretty much for today's lecture. You have any questions for me? Okay, I assume it's a no. So in that case, I hope you guys enjoy the rest of the weekend, and I'll see you guys for next week. Bye, guys.